Welcome to this lecture on the properties of the Fourier transform. So the learning outcomes of this session are you should be able to understand the properties of the Fourier transform, and you should be able to prove the various properties of the Fourier transform. Now we are simply reviewing the equation for the Fourier transform. The Fourier transform is simply given as capital X of f, which is a integral minus infinity to infinity x of t e power minus j 2 pi f t dt. Now here we have listed the various properties of the Fourier transform: linearity property, time reversal property, duality property. Now here we are also listing the time shifting property, the frequency shifting property, the time scaling property, and differentiation property. And here some other properties: the integration property, convolution property, and modulation property. Now we are going to prove these properties. So first we are going to prove the linearity property. The linearity property states that if we give a composite signal or a linear combination signal a x1t plus b x2t, the Fourier transform will also be a linear combination of a x1f plus b x2f. Now let us prove this property. So we take a x1 plus b x2 as a new signal z of t. Then the Fourier transform of that new signal, capital Z of f, is simply the integral z of t e power minus j 2 pi f t dt. Now we are going to substitute z as a x1 of t plus b x2 of t, and then we write the e power minus j 2 pi f t, that exponential factor, and also the integral variable dt. Then we can factor this integral into two pieces. The first piece is the integral of ax1 into e power minus j 2 pi f t dt, plus the second piece is the integral of this bx2 multiplied by e power minus j 2 pi f t dt. Now here the integration is with respect to t. Here a is a constant, so the constant is going to come out of the integral. Then we are left with the integral of x1 of t e power minus j 2 pi f t dt. That is simply the Fourier transform of x1 of t, which will be x1 of f, which is multiplied by a, plus the second piece is simply b, which is multiplied by this integral. Again, this second integral is the Fourier transform of x2 of t. Therefore, this second integral will be x2 of f, that is multiplied by b. Henceforth, we get the final answer. The Fourier transform of this composite signal or linear combination signal ax1t plus bx2t is simply another linear combination of individual Fourier transforms ax1f plus bx2f. Now we are going to prove another property, which is the time reversal property. The time reversal property states that if we give the signal x of minus t, which is the time reverse signal, then the Fourier transform will be capital X of minus f. So we have to replace the variable f with minus f. So it's a very simple property. So we are going to take the Fourier transform of that signal x of minus t, which is simply the integral x of minus t multiplied by e power minus j 2 pi f t dt. Then we substitute that variable minus t as m. Therefore, we will get dt, this variable of integration dt, it becomes minus dm. And then as t tends to infinity, m will tend to minus infinity. Therefore, the integral limits will be reversed, and we get the lower limit as infinity and upper limit as minus infinity, and x of minus t becomes x of m, and we have e power minus j 2 pi f. In the place of t we have to write minus m, and in place of dt we have to write minus dm. Now whatever is this integral limits that got reversed and this minus dm, they cancel each other, and this integral can be simplified as the integral minus infinity to infinity x of m e power minus j minus f of m into dm. So if we compare this equation with a Fourier transform, we can simply see this m is a dummy variable, and here in place of f there is minus f. Therefore, this is a Fourier transform with minus f. Therefore, the output is capital X of minus f. Now we are going to discuss another property, time scaling property of the Fourier transform. So if we give the signal x of at, then the Fourier transform will be 1 by a capital X of f by a. Now we will prove this property. So we are going to write the Fourier transform as the integral whatever is the new variable x of at we are taking as z of t multiplied by e power minus j 2 pi f t dt. Then here we are going to substitute whatever is that at as a new variable m. Therefore we will get t as m by a, and the variable of integration dt will be dm by a. And we can simplify this equation as in the place of z of t which is x of at becomes m, so we will get x of m, then e power minus j 2 pi f. In the place of t we have to write m by a, and uh, in the place of dt we will get dm by a. Therefore here the constant 1 by a will come outside, and we can write the integral as the integral x of m e power minus j 2 by f by a m multiplied by dm. So in place of f you are now having f by a. Therefore this is the Fourier transform where f is replaced by f by a. Therefore we will get 1 by a, this constant factor, and this integral is simply capital X of f by a. So if we are taking the Fourier transform of the time scaled signal x of at, whatever is the scaling factor, that 1 by a is coming as a multiplication factor, and even the frequency is getting multiplied by the scaling factor. Now we are going to discuss the time shifting property. Now if you take the signal x of t minus capital Tp, the Fourier transform will be e power minus j 2 pi f Tp multiplied by capital X of f. So the original Fourier transform capital X of f is simply multiplied by this exponential function. So let us prove this property. So we will take this integral minus infinity to infinity x of t minus Tp into e power minus j 2 by f t dt. Now we are going to replace that time shifting factor t minus Tp as a new variable m. Then we will get t as m plus Tp. Then dt will be of course dm. Then we can write this integral as x of m e power minus j 2 pi f. In the place of t, wherever you have t, you have to write m plus Tp. So you are going to get m plus Tp, and dm in place of dt. So we can factor this e power a plus b as e power a into e power b. Now the variable of integration here is dm. Therefore this function e power minus j 2 pi f Tp, which is not having the variable of integration m, this function e power minus j 2 pi f Tp, because it is not containing the variable of integration m, it becomes a constant, and it will come out of the integral, and the rest of the integral x of m e power minus j 2 pi f m dm is simply the Fourier transform, which is capital X of f. We are going to prove another property which is the frequency shifting property. Here we take the signal x of t and multiply with the exponential function e power j 2 pi f naught t. Then the Fourier transform on the output side will be x of f minus f naught. So we are having a frequency shift that is occurring when we multiply the input signal with the exponential function. Now let us try to prove this property. So we are going to take this entire signal and multiply with e power minus j 2 pi f t dt and do the integration. Now we can combine these two exponential factors e power a into e power b as e power a plus b. Now here we are taking this minus as a common factor. So we are going to get minus j 2 pi f minus f naught. Now if we simply compare this equation with the regular Fourier transform, which is x of t e power minus j 2 pi f t dt, we can see in the place of f we have f minus f naught. So this above integral is simply capital X of f minus f naught, and hence we have proved the property. So if we take the Fourier transform of this signal e power j 2 pi f naught t multiplied by x of t, we are getting capital X of f minus f naught. Next we are going to prove a very important property, which is the duality property. So if you take the signal x of t, let us say its Fourier transform is capital X of f. Now we are going to give that function capital X of f, but in the place of f we are going to write the time variable. So the function is capital X of t, and then take its Fourier transform. You are going to get small x of minus f, where whatever is this small x of t, the input to the Fourier transform, that small x where we have replaced the t with minus f. Now we are going to prove this property by taking the inverse Fourier transform. The inverse Fourier transform is simply x of t is equal to integral capital X of f e power plus j 2 pi f t df. Now we are going to simply interchange the variables t and f in the above equation. So wherever t is there, we have to write f, and vice versa. So here t is there, we have to replace t with f. So you'll get small x of f. Now integral is as it is. Here it is capital X of f. We have to replace with t. So you get capital X of t. And here e power minus j 2 pi ft, we replace f with t and t with f. We again get the same factor. Then df becomes dt. Next we are going to replace f with minus f. So always remember, we are having these equations, and these equations are having certain symbols. The symbol t is a particular letter in alphabet. We can always replace the t with f. Same thing, the number f can again be replaced with minus f. Okay. So now we are doing the second substitution. We are replacing f with minus f. So here in place of x of f, you will get x of minus f, and which will be equal to this integral. X of t will stay as it is, capital X of t. Then you will get e power 2j. Then in the place of f, we are going to write minus f. T stands as it is. Dt remains the same as it is. Then we can write this equation as integral x of t e power minus j 2 pi f t dt. This is simply the Fourier transform of the signal capital X of t. So thus we can see the Fourier transform of the signal capital X of t is simply small x of minus f. That's what is the duality property. Now we are going to discuss another property, which is differentiation in time property. So if you take the signal d by dt of x of t, then the Fourier transform will be j 2 pi f multiplied by capital X of f. Now we are going to prove this property by taking the inverse Fourier transform as we did before. So we are going to take the inverse Fourier transform x of t is the integral capital X of f multiplied by e power plus j 2 pi f t df. Now we are going to take the derivative with respect to the time on both sides of this equation. Then we are going to get d by dt of x of t, which will be equal to the d by dt of this Fourier inverse Fourier transform equation. So we'll get d by dt, this entire inverse Fourier transform equation. Now here the integration is having these variables of f and t, but the derivative is with respect to d by dt. So capital X of f will be a constant, df will be constant. We have to apply this derivative d by dt to e power j 2 pi ft, which is having the t variable. So when we take this derivative, the derivative will apply only to the e power function because it is having that derivative variable t. Now, if you take the derivative of that e power function, you are going to get j 2 pi f multiplied by again that e power function e power j 2 pi ft, and whatever is the integral and capital X of f df, they remain as constants. Then we can simply combine this j 2 pi f and x of f as a single factor. This integration can be rewritten as integral minus infinity to infinity, same as before. Now we are combining this x of f and j 2 pi f. So we will write x of f and j 2 pi f as a single factor, which is multiplied by that e power j 2 pi ft, and the df variable is coming. Now if you see this, this is simply the inverse Fourier transform of j 2 pi f multiplied by capital X of f. Therefore, we can observe that the inverse Fourier transform of capital X of f multiplied by j 2 pi f is d by dt of x of t, which is the differentiation in time property. Now we are going to prove the integration property. This integration property is reverse or reciprocal of the differentiation property. So if we take the integral of x of tau d tau, then its Fourier transform will be capital X of f divided by j 2 pi f. So what we do is we consider this integral minus infinity to t x of tau d tau as a new variable, and we are going to take the derivative with respect to the time t. So then whatever is this derivative d by dt of z of t, which is the d by dt of the integral of x of t, then the integral and the derivative will cancel each other. We will get x of t back. Now if we take the Fourier transform of z of t as capital Z of f, then we can use the differentiation property, because d by dt of z of t is x of t. So by using the previous differentiation property, we can apply the Fourier transform on d by dt of z of t, and that will be j 2 pi f into capital Z of f, which should be equal to the Fourier transform on the RHS is what? X of t. The Fourier transform of x of t will be capital X of f. Therefore, we can get Z of f as capital X of f divided by j 2 pi f. Therefore, whatever is this capital Z of f, it is simply the Fourier transform of this integral. Therefore, if we take this integral and take the Fourier transform, we are going to get capital X of f divided by j 2 pi f. Now we are going to discuss a little bit more in detail about this integration property. Now let us consider the special case of f equal to 0. Then in the previous integration property, whatever is the result, capital X of f divided by j 2 pi f will become infinity, unless this capital X of 0 is 0 at f equal to 0. Now if capital X of f is 0, then the integral will evaluate to 0. and there is no problem of infinity. Therefore, if this capital X of 0 is 0, so we have to simply substitute in this Fourier transform equation f as 0. Then this e power 0 becomes 1, that is simply the integral of x of t into 1, which is simply the integral of x of t, that will be equal to 0. Now if we are taking this integral of x of t equal to 0, it is the time average, because we are integrating that signal. Okay, so the previous property, the integration property, it holds for the signals whose time average is 0, so that whenever, for the special case where f is equal to 0, this capital X of f will be 0, and there is no issue of the infinity calculation. Now we have to remember the previously discussed integration property, that the Fourier transform of the integral of x of t will be capital X of f divided by j2 pi f. It holds only for those signals whose time average is 0. Now for several signals that time average is not always 0, for those type of signals the integration property is modified by adding a delta function at f equal to 0 as shown below. So the Fourier transform for the more general case, if we discuss the integration property, the Fourier transform of the integral of x of t will be capital X of f divided by j2 pi f plus the delta f multiplied by capital X of 0 divided by 2. So we are adding a delta function to the more general case where the signal's time average is non-zero. So this is a more general integration property that even applies for all the signals whose time average is non-zero. Now we are going to prove another property, very important property, which is the convolution property. So if we take the Fourier transform of the convolution of x1 of t, x2 of t, then we get the multiplication of individual Fourier transforms capital X1 of f with capital X2 of f. Now let us take this Fourier transform of this convolution. Therefore, we will get the integral x1 of t convolved with x2 of t multiplied by that e power function e power minus j2 by ft dt. Then this convolution we are going to write using the convolution integral formula, integral minus infinity to infinity x1 of tau x2 of t minus tau d tau. Therefore, we are now going to substitute this integral into the Fourier transform equation. Then we will get a double integral. Okay, because already this convolution integral is having one integral, and Fourier transform is also having a integral. Okay, so we are going to get a double integral, and then inside the integral we are going to get this x1 of tau multiplied by x2 of t minus tau d tau, then followed by this Fourier transform factor e power minus j2 by ft dt. Now we can write this as two integrals, integral of x1 of tau and this factor d tau multiplied by the second integral and x2 of t minus tau e power minus j 2 pi ft dt. So we have simply separated this double integral as two integrals. One is the integral with d tau, the other is the integral with dt. Now we are going to simply substitute t minus tau as m. Therefore, we can write the first part of the integral as it is, integral x1 of tau d tau. Then the second integral is x2 of, earlier it was t minus tau, now that becomes x2 of m. then e power minus j 2 pi f t. In the place of t we have to write m plus tau, and then in the place of dt we will write dm. Now here we have this e power a plus b, we can factor it as e power a into e power b. Now we will rearrange these exponential factors. We will have here the exponential factor with tau. So we will take this and combine with the first integral where you have d tau. Okay. So then we are going to get again the two integrals. Integral x1 of tau e power minus j 2 pi f tau d tau. Now this is nothing but the Fourier transform of x1 of t. You should always remember this tau or t is a dummy variable because it's a definite integral. Finally this tau will be replaced by infinity and minus infinity. Okay, so this first integral is simply x1 of f. Now the second integral, again if you see, this is also the Fourier transform of x2 of t, because again m is a dummy variable, and this will be capital X2 of f, this entire integral. Therefore we are getting the final result. The first integral is simply capital X1 of f multiplied by the second integral is simply capital X2 of f. Therefore if you take the convolution signal x1 of t convolved with x2 of t, the Fourier transform will be the multiplication of individual Fourier transforms, capital x1 of f multiplied with capital x2 of f. Thank you very much.